what happened was the LHC discovered the Higgs boson in 2012, and soon afterwards it closed down for 2 years. It had an upgrade, and last year in 2015, the LHC turned on again with twice the energy that it had when it discovered the Higgs. And the goal was twofold. The goal was firstly to understand the Higgs better, which it's done fantastically, and secondly to discover new physics that lies beyond the Higgs, new physics beyond the standard model. So before I tell you what it's seen, let me tell you some of the ideas we had, some of our expectations and hopes for what would happen moving forward. So this is our favorite equation again. The idea has always been the following. You know, if you're a Victorian scientist and you go back and you look at the periodic table of elements, then it's true that there's patterns in there that give a hint of the structure that lies underneath. Okay, there's numbers that repeat themselves. Where if you're very smart, you might start to realize that, you know, yes, there is something deeper than just these elements. So our hope as theorists is to look at this equation and see if maybe we can just find patterns in this equation that suggest there might be something deeper that lies underneath. And they're there. So let me give you an example. This is the equation that describes the force of electricity and magnetism. And it's almost the same as the equations which describe the forces for the strong force and the weak nuclear force. Okay? In fact, you can see I've just changed letters. Okay? It's a little more complicated than that, but it's not much more complicated than that. The three forces really look similar. So you might wonder, well, maybe there's not three forces in the universe. Maybe those three forces are actually just one force, and when we think there's three forces, it's because we're looking at that one force just from slightly different perspectives. Maybe. Here's something else which is amazing. These are the equations for the 12 matter fields in the universe, the neutrinos, the electrons, and the quarks. Each of them obeys exactly the same equation. Each of them obeys the Dirac equation. So again, you might wonder that, well, maybe there aren't 12 different fields. Maybe they're all the same field and the same particle. And the fact they look different is, again, maybe just because we're looking at them from slightly different perspectives. Maybe. So these ideas that I've been suggesting go by the name of unification. The idea that the three forces are actually combined into one is what's called grand unification. And it's very easy. It's very easy to write down a mathematical theory in which all of these are just one force, which appears to be three from our perspective. Okay. There are other possibilities here. You might say, well, this is the matter, and these are the forces, and the equations are different, but they're not that different, because ultimately they're both just fields. So you might wonder if maybe there's some way in which the matter and the forces are related to each other. Well, we have a theory for that as well. It's a theory that's called supersymmetry. And it's a beautiful theory. It's very deep conceptually, and it sort of smells like it might be right. Finally, you might be really, really bold. You might say, well, can I just combine the lot? Can I just get rid of all of these terms and just write down one single term from which everything else emerges? Gravity, the forces, the particles, the Higgs, everything. Well, I've got something for you if you want that as well. It's called string theory. So we have a possibility for a theory which contains all of this in one simple concept. And the question going forward, of course, is are these right? It's very easy for us theorists to have these ideas. And I should say, these ideas are what's driven theoretical physics for 30 years, but we want to know, are they right? And we've got a way of telling they're right. We do experiments. So I should say, if you want to know if string theory is right, we don't have any way to test it at the moment. But if you want to know if some of these other ideas are right, then that's what the LHC should be doing. The reason that we built the LHC was firstly to find the Higgs, okay, it worked, and secondly to test these kind of ideas that we've been having to see what lies beyond. So the LHC has been running, it's been running for 2 years, it's been running like an absolute dream. It's a perfect machine. 2 years, this is what it's seen. Absolutely nothing. Okay? All of these fantastic, beautiful ideas that we've had, none of them are showing up at all. And the question going forward is, what are we going to do about it? How are we going to make progress in understanding the next layer of physics when the LHC isn't seeing anything and our ideas just don't appear to be the way that nature works? Okay. I should tell you upfront, I don't have a good answer to this. I say my impression is that most of my community is a little bit shell-shocked by what happened. There's certainly no consensus in the community to move forward, but I think there's three responses that sort of various people have had that I'd like to share with you. And I think all three of these responses are reasonable up to a point. The first response to the LHC not seeing anything is the following. It's well, you young kids, you're so pessimistic. It's all doom and gloom with you. You need a little bit more patience. It didn't see anything last year and it didn't see anything this year, but next year it's going to see something. And if not next year, it's the year after that it's going to see something. It's usually my very illustrious senior colleagues that have this response. And you know what? They could easily be right. It could easily be that next year the LHC discovers something astonishing and it sets us on the path to understanding the next layer of reality. But it's also true that these same people were predicting that it would have seen something by now. And it's also true that this can't keep going for much longer. If the LHC doesn't see something within, say, a 2-year timescale, it seems very, very unlikely that it's going to see something moving forward. It's possible, it just seems unlikely. So, we'll know, I hope with all my heart that the LHC discovers something next year or the year after, but I think we have to prepare for the worst, that maybe it won't. Okay, response number two. Which is sort of also by similar people. Well, all our theories are so beautiful, they absolutely have to be correct, and what we really need is a bigger machine. Okay? 10 times bigger, we'll do it. Okay, again, they might be right. I don't have a good argument against it. The obvious rebuttal, however, is that a new machine costs $10 billion. And there's not too many governments in the world that have $10 billion to spare for us to explore these ideas. There's one. The one is China. And so if this machine is going to be built at all, it's going to be built by the Chinese government. I think the Chinese government would see it as extremely attractive if the whole community of particle physicists and engineers that are currently based in CERN in Geneva move to a town that's slightly north of Beijing. I think they'd view that as a political and economic gain, and there's a real chance that they may decide to build this machine. If they do, it's about 20 years for it to be built. So we're waiting slightly longer. There's a third response, and I should say the third response is kind of the camp I'm in. I should mention up front, it's speculative, and it's probably not endorsed by most of my peers. So this is really just my personal opinion at this point. This is my take on this. This is the equation that we know is right. This is sort of the bedrock of our understanding. But although we know it's right, there's an awful lot in this equation that we haven't understood. There's an awful lot, to me, that's still mysterious in this equation. So although this equation looked like there were suggestions of unification, maybe they're just red herrings. And maybe if we just work harder and trying to understand this equation more, we'll find that there are other patterns that emerge. So my response is, I think that maybe we should just go back to the drawing board and start to challenge some of the assumptions and paradigms that we've been holding for the past 30 years. So I should admit, I feel quite energized, actually, by the lack of results for the LHC. I sort of, it feels good to me that everyone was wrong. It's when we're wrong that we start to make progress. So I sort of feel quite happy about this, and think that there's a very real chance that we could just start thinking about different ideas. I should say that there are hints in here. There are hints to me about mathematical patterns that we haven't explored. That there's hints in this about connections to other areas of science, things like condensed matter physics, which is the science of how materials work, or quantum information science, which is the attempt to build a quantum computer. All of these fantastic subjects have new ideas which sort of feed in to the kind of questions that we're asking here. So I'm quite optimistic that moving forward, we can make progress. Maybe not the progress that we thought we'd make a few years ago, but just something new. So that's the punchline of my talk. The punchline is that this is the single greatest equation that we've ever written down. But I hope that someday we can give you something better. Thank you for your attention.